so we're talking about rational numbers. So what is the definition of what is a rational number? How can you know if a number is rational? Yes.
If it can be represented as a ratio.
A ratio of?
Two integers.
Good. Okay, so rational number. So a number is rational if it can be represented by, as a ratio of two integers. All right, good. And so, like the Xi book gives you ones like, hey, could you do, 6.2? Okay, and hopefully that's pretty easy. Like, if you wanted to represent 6.2 as a ratio of two integers, what would those integers be? Do the most obvious one. Sorry, what? Is 6.2 an integer? No. 62 over 10. Okay, so make sure they're integers. Yeah, so 62 over 10, okay. Okay, so it can definitely be represented as a ratio of two integers. Make sure they're integers. Okay, so that is good, but all the ones that your book, the Xi book gives you are terminating decimals. But also every repeating decimal can be written as a ratio of integers, but the book doesn't give you any of those, so I think we should practice. Okay, so for example, like that 0.3 repeating can be represented as a ratio of integers. What ratio of integers would you choose for that one? 33 over 99 is the least obvious one, but yes, it is. Yes. It also is 1/3, but But sometimes it's fun to be exciting. Like 33 over 99 is fun too. Okay. So yes. So it is 1/3 or 3/9, however you want to think of it. So some of them you've probably memorized, but then but if I give you like 0.205 repeating, okay, you probably don't have that one memorized, neither do I. I just made it up. Okay, I have no idea what it is. We're going to have to discover it together. Okay, so let's review the steps of how I would go about figuring out what integers I could put in a ratio to give me 0.205 repeating. Okay, so I always start with n being what my number is. Okay, and what's the first thing that I want to do? Good thing we're reviewing this. Okay, the first thing that we want to do is we want to multiply our number by something so that the decimal point is in front of just the part that repeats. Okay, so you want to isolate just the repeating part of it. Okay, so what would I have to multiply both sides of this by to move my decimal point so it's just in front of the part that repeats? 100. So I'd multiply this side by 100. When I multiply the other side by 100, I get 20.5 repeating. Okay. So that's my first step, is to make sure that I multiply both sides by something so that the decimal point is in front of just the repeating part. Okay, and then my goal is to then take this and move the decimal point past one section of the things that repeat. So I just look at how many digits are repeating. There's just one of them. So to move it past that one digit, I would have to multiply both sides of this by 10. So on this side I would get 1000n, and on this side I would get 205.5 repeating. There's an infinite number of 5s, so the 5s are continue to repeat. Okay. But the nice thing about this is now I have these repeating things, and if I subtract these numbers, all the repeating stuff goes away, and I'm left with an integer, right? So that is why I did all of this. Okay, so if I subtract, I'm just going to write this out. So I'm going to do 1000n minus 100n. So I'm doing the bottom one minus the top one. Okay. And so that will be 205.5 repeating minus 20.5 repeating, and I guess I'll get 185. Okay, so 1,000 minus 100 is 900. And so n is 185 over 900. And you don't have to reduce these. Let me grab my calculator. Okay, and you can always check yourself and make sure that you did it right by just doing, look, 2055555, and it ran out. It can't go forever, so it'll round, but you know it really means that it's going on forever, right? Okay. So, you can just make up your own problems. Yes, there aren't any like this in the Xi book, but all you need is a calculator to check yourself and see if you're right. You just make up your favorite, you just use your favorite numbers. Let's do one more. Okay, so, all right. Vaughn, what's your favorite integer?
552.
552, okay. Let's see. Carlos, what's your favorite two-digit number? If I just say integer, you might give me too many digits that I don't want to deal with. 42. 42. Oh, yeah, that's a good one. I like 42. Okay. Okay, and then, all right. Austin, how many digits do you want to repeat? 2, 3, 4? 2. We're going to have these last two repeat. Okay. So, all right. So this is our n. What should we multiply by first? 1,000. All right, so we'll do 1,000, and that will move our decimal point 3 places right in front of the part that repeats. And then what should I multiply both sides of that, of the next one by? Okay, I hear 10 and I hear 100. So if I multiply by 10, it's going to put my decimal point in the middle of the repeating. If I multiply by 100, it'll move past the whole group of repeating. I want to make sure it goes past the whole group of what's repeating. So I've got 2 digits repeating. I better multiply by 100. So yes, I want to multiply by 100, not by 10. Okay, so there were already 3 zeros. I'm adding 2 more of them. And I'm going to get 55242.42 repeating. Right? So I want to make sure that whatever I have here, as far as my repeating are the same. If I only multiplied it by 10, I would have a 2-4 repeating, not a 4-2 repeating. Okay, and then I wouldn't be able to subtract it and get rid of it. Okay, so it's very important that I do the 4-2. All right, so let's see. Okay. 55242 minus 552. All right, so on this side I have a 54690. And on this side, 1, 2, 3, I've got what, a 9. How many 9s should I have? 3? 0. I think that's right. Okay, and so my n would be the 54690 over the 99,000. I can even just reduce it a little bit. Okay, and let's see if I have 54690 divided by 9,900. I get 552424244. Okay, so well. It's the 42424242 that's repeating. Okay. All right. So that is how you do those. They're not that hard to do. You just have to know how to do them, and you probably just need to practice a few. Just just make up random numbers, try them out, and just you can always check them with your calculator and see if you got them correct. You might want to bring your calculator tomorrow, just in case, yeah. Not tomorrow. Tomorrow meaning the next time tomorrow is an abstract idea for the next time that we meet together as a class. Yeah.
What sections are going to be on the testing Tuesday?
It's up through 3.4, so I think it's it's the last 4 sections of chapter 2. Is that 2, 9, 10, 11, 12, or is it 8, 9, 10? I can't remember.
Is that a quiz or is it
1.9 through 3.4. Yeah, it's on the study guide. Yeah, so at 1.9, yes, that's right. So there's like 1.9, 10, 11. Is there 12 as well? Yeah, there's 4 sections in chapter 1. So that's basically over nested quantifiers and logical reasoning. Okay. So those are basically the 2 subjects from the logic, and then there's all of sets. And then
So the notice pony stuff, when you provide the sheet for that?
yes. Yeah, and yeah, so like the modus ponens, modus tollens, disjunctive syllogism, that whole bunch of stuff is it'll be on there. Yes.
Is it a study guide?
Yeah, it's on. Yeah, I posted it like 2 weeks ago or something. Yeah, it's on iLearn. It's kind of there's several announcements that have come after it, so you might have to kind of go backwards in the announcements because it's been up there for a while. Oh, it is at the top of announcements?
On mine it is.
Okay. All right. So. Okay. Any other questions? Okay. All right. So as far as the test goes, it covers all the stuff that's on the study guide, really, like the major biggies that are on there. So just make sure that you look at everything on the study guide. We haven't been quizzed over like Cartesian products and partitions, so make sure that you look at those things. Those are basically the last couple of things that weren't on the quiz that we did over sets. Make sure you go over the quiz that we had on sets and you understand the difference between a subset and an element, because you're going to see it again. Okay, so you make sure that you need to know the difference and the little, what's the difference between an empty set and a subset containing the empty set, and which one of those is in the power set? Is it the empty set or the subset containing the empty set? Which one is in the power set? Just the empty set. So make sure you don't put that empty set in a subset, because it's just the empty set. Yeah. So make sure that you look at the little details of those things as well that are easy to get mixed up on. Okay. All right. And of course, there will be a direct proof, so we should practice some of those, like this one. Okay. All right. So last time we were talking about direct proofs. We've just got a couple more examples that we want to work through before we go on to the next type of proof. Okay, so we have a proof that if x and y are rational numbers, then y over 1 minus 1 over x, that crazy complex fraction, is also a rational number. Okay. So we already we know that if I want to prove that something is a rational number, I have to show that it can be written as a ratio of 2 integers. Okay. So that's kind of what we're, in terms of big picture, what we have to be thinking about. Okay. All right. So, I'll see what you guys can remember. What should I start? What is the first thing I should do in my direct proof? Good. Start with our assumptions. So assume that x and y are rational numbers. Okay. And if you kind of do them all the same, kind of get yourself a recipe or a little algorithm of how to do these, they go a little bit quicker. So usually what's a good thing to do next? Yep, go ahead, Carlos.
Say we will prove that y over 1 minus 1x is also a rational number.
Good. so we will prove that y over 1 minus 1 over x is also a rational number. Okay. And so we have to now start with our assumptions and, you know, figure out what things that we could logically conclude from any definitions, theorems, rules of algebra, that kind of stuff that we know. So what probably should we do first? Okay.
We do, like, since x and y are rational, they can be written as variables you pick.
Good. Let's just do A, B, C, D. That's easy. Okay, since x and y are rational, there exist A, B, C, D that are integers. Okay, and let's B not equal to 0, D not equal to 0, because I'll make those our denominators such that x equals A over B and y equals C over D. Good. So that we can start with that, and now probably it's a good idea to go and look at this thing that we're trying to prove something about. Okay. And we know, like, what we might want to simplify this one first. Okay, let's just say the expression, okay, y over 1 minus 1 over x simplifies to, okay, what would we do to simplify that? This is where your algebra skills come in handy. Anyone? Yes?
Can you rewrite it as y over x minus 1 over x?
Okay, good. So it'll be the long way around. So yes, that is correct. And then what would you do after that?
Multiply it by the reciprocal.
Okay, that's good. So that's one way of going about it. Can I just do a little side note here? Okay, so we had our y over 1 minus 1 over x. So Josh's idea is rewrite the denominator as a single fraction. So we could rewrite that as x minus 1 over x. Okay, and then after you have that, then you go, oh, well, if I have something divided by a fraction, that's just the same thing as the numerator multiplied by the reciprocal of the denominator. And so I would get xy over x minus 1. So it simplifies to that. I personally think it's easier, okay, to look at all the denominators. Well, this has a denominator of 1, this has a denominator of 1, this has a denominator of x. Then take the least common denominator of all of the denominators, or the least common multiple of all the denominators, which is x, and just multiply by x over x. Okay, so here I get xy, and when I distribute there, x times 1 is x, and x times 1 over x is 1. You can get it in one step instead of going the long chain. So, I mean, it's not wrong to do that. I just think it's simpler to do that. So, I don't care how you get there, but it simplifies to xy over x minus 1.
Could you also prove it with a limit?
Oh, that'll be fun. No, I don't know. I think that's overkill. What are you gonna do? Limit is, what limit are you gonna use?
Every time I see 1 over x, I always think of limit.
No, I don't know. I'd have to think about that. Could I throw some limits in here? I don't know. No, I just think all you need is algebra. Okay. Okay, so, but I think that it's easier for us to work with this because the next thing we're gonna need to do is substitute these values in for x and y, and we're gonna get complex fractions again, but it would have been worse if we had, had to substitute a over b in this fraction, and then we'd have these like 3 layers of fractions deep, so, okay. All right, so I'm going to label this 1 and this 2, and I'm going to Okay. So that substituting 1 and 2 into the above expression gives that this is equal to, alright, so x is a over b, y is c over d, x is still a over b minus 1. Okay, and here's where looking at the denominators and multiplying by least common multiple over least common multiple, okay, will make things a little bit easier. So all the denominators are B, D, and B. What's the least common multiple of B, D, and B, and well, and 1? What should I multiply by? Whatever, what? Yeah, BD over BD. Okay, and so when I do that, the B and the D will cancel out. I'll just be left with AC in the numerator. And when I, don't forget, you probably want to write parentheses on that one so you can remember you have to distribute this to both of those. So when I multiply it by the first one, I'll get AD, and then when I multiply that BD by 1, I'll get minus BD. Okay. And now that is really nice because, okay, I have this xy over x minus 1 written as a ratio, and if I can just prove that these two things are both integers, then it's a ratio of integers. So the last thing I have to do is make an argument that this ratio actually fits the definition of rational numbers and that it is a ratio of integers. So first of all, is AC in the numerator an integer?
Yes.
Yes, because why?
Because A and C are both integers and they're closed for multiplication.
Yes, so since Z is closed under multiplication, AC is an integer. Okay. And then what about the denominator, the AD minus BD? So we've already established that these two, the A times D and the B times D, that's multiplication. But we also have the subtraction, since it's also closed under subtraction. That AD minus BD is also an integer. Okay. Thus, by definition, xy over x minus 1, oops, which is equal, sorry, I should have just put this original one. You don't need that one. Okay, is a rational number. Okay, and that's what I set out to prove, that it's a rational number, and so I'm done. Yes.
What section was the multiplication for substitution?
That was in 3 point, I can't remember if it was 1 or 2. But at the beginning of the beginning of the chapter 3 on proofs. So there were like 3 sections in proofs. One that had definitions and what you're allowed to use, and one of the things is the closure properties of integers. So we talked about the fact that the integers are closed under addition and subtraction and multiplication, and that they're not closed under division.
Sorry, what does it mean to be able to close?
Okay, oh, good question. Yeah, that's a very good question. Can anybody answer it? What does it mean that it's closed? Yeah.
It can't change to any other, I want to say set, but I know that's not the right word. Is it like
Yeah.
As in like real numbers, whole numbers, integers, and then ratios. I don't know how to explain it in words, but
Yeah, I think you're on the right track. So being close said if I take two things from the set and then I apply the operator to them, the answer that I get will also be in that set. Okay, and so for instance, it's closed under addition because if I take an integer and another integer and then I add them, the answer that I get will always be an integer. There's no way for it to be something else that's not an integer. Okay, but remember we said it's not closed under division. So if I take an integer and another integer and I divide them, can I guarantee that the answer is always an integer? No, because if I take 2 and divide it by 5, I get 2/5, which is not an integer, right? Yeah, so it's not closed under division, but multiplication, addition, and subtraction, any of those operations, if you use that operation on two integers, you always get an integer as an answer. That's what it means for it to be closed.
And I guess, so going off of what we really have right now, would there ever be a time where it would, like, would it be closed under subtraction or not really?
So if we said, prove that if x and y, if there was something about natural numbers, for example, so natural numbers are not closed under subtraction. Because if you take one natural number and you subtract another natural number, you can't guarantee that it's always a natural number. For example, again, 2 and 5. If I take 2 and I subtract 5, the answer is not a natural number. It's -3, and so there's no negatives in the natural numbers, right? So for integers, we have to know the closure properties for integers. Integers are closed under addition, subtraction, multiplication. But if there's, if there's a different problem and it was a proof about natural numbers, then we'd have to be careful because that one's only closed under addition and multiplication, but not under subtraction or division.
Okay.
Yeah. Yes.
So since we already stated that it's closed under multiplication, do we not have to state AD and BD? Or is that just under subtraction?
Well, the AD we already stated multiplication here. So we got AD and BD. I'm just combining the multiplication and the subtraction all into one.
Like restate it?
Yeah, we don't need to restate it. Okay. Yep.
What would happen if like A and B were equal to each other? Would that denominator not equal 0 there? Would that?
If A and B were equal to each other,
Yeah.
oh, there is no D here. This is wrong, isn't it? It's just A. No, it's for AD. So if A and B were equal to each other, that's a good question. Yeah, we have no guarantee that A and B aren't equal to each other. Yeah, yeah, you're right, because if this was a 1, if A and B were equal, we'd have a ratio. So, I think that we'd have to just say, we'd have to add this, you found an error. This is an example from the Xi book, but yeah, they should have put, this is only rational when x is not equal to 1. Okay. That's an excluded value. It should have been listed because it's, undefined. If x is equal to 1, it's not a rational number. So, very good catch. So, we would probably have to put in here that a is not equal to b. Yep, good catch.
Did you also say the same thing for C and D, make sure C is not equal to D?
That doesn't matter if C and D are equal, just the A, because this can't be 1. So x can't be equal to 1, so we just have to make sure that this, it doesn't matter if these are equal, because y being 1 doesn't give us a problem. The thing that gives us a problem is x being 1, because then we have 1 minus 1, which is 0 in the denominator, and zeros in denominators are bad. Yeah. Yeah, so that should have been specified as part of the original statement of the problem. Yeah. Good. Okay, anything else? Jared gets the gold star of the day for finding the error in the proof, what we were supposed to prove. Okay. All right. Next one, prove that if x is a real number that's less than or equal to 2, then x squared minus 7x plus 10 has to be greater than or equal to 0. Okay. So, just like last time, we start with our assumptions. So what do we assume? Yeah. X is a real number such that x is less than or equal to 2. Okay. And then we will show that x squared minus 7x plus 10 has to be greater than or equal to 0. Okay. Okay. So, if you ever see any of these that have these kind of inequalities, okay, so what you want to be thinking about is when you have things that are multiplied together and you know the signs of them, you can, it's like I know that a negative times a negative is a positive. I know that a positive times a positive is a positive. I know that a negative times a positive is a negative. So these kinds of things can be very helpful. Okay, so, but right now I don't have any things that are multiplied together so that for me to reason about whether the kind of a product would be positive or negative. But if I factor, then I will have a product. Okay, so if I look at this right here, it would be really nice if I could factor that so that it's written as a product of two things that are multiplied together. And then if I knew the sign of those two of the factors, then I could make an argument about the product. So let's start by factoring. We factor to obtain, okay, what, oops, sorry, should be greater than or equal to 0. So what does this thing factor into? X minus 5 and x minus 2. Okay. All right, so since x is less than or equal to 2, what can we say about x minus 2? This factor, that's the easiest one to think about. It's less than or equal to 0, right? Just subtract 2 from both sides. We just change that inequality. All right, so we know that x minus 2 is less than or equal to 0. Does that mean that it's negative? No, what's the word for it? It's not negative, it's non-positive. All right, so x minus 2 is non-positive. Okay, it could, okay, it's either negative or 0, but it's non-positive. Okay, what about this x minus 5? I mean, so like from this, if I subtracted 3 from this side and subtracted 3 from this side, x minus 5, okay, is less than or equal to negative 3, and negative 3 is less than 0, right? So what can we say about x minus 5? Is that negative? Yeah. So this one, okay, let me put here. So x minus 2 is non-positive. Okay, and here, so x minus 5 is negative. Okay. And up here, I have a negative number times a non-positive number. Okay. If I multiply a negative and a non-positive, what can I guarantee that the product is? non-negative. Okay. Okay, so the product x minus 5, x minus 2 will be non-negative. In other words, x minus 5 times x minus 2 has to be greater than or equal to 0. It's non-negative. Okay. And that should be enough. This is the same thing as that. We have shown what we have. If you wanted to rewrite that multiplied out again, you could, but that's not necessary. Okay. So in any of the inequalities, it's often a good idea to try to use the signs of things as part of your argument. Okay. Yes?
So given a polynomial that we, or quadratic that we can't factor, could we just show that, like, if you plugged in, just like with this, anything, any negative number squared would be positive, and any negative number times negative 7 would be positive, so could you show those and prove it that way?
Yeah, you could do that, but so you'd have to make sort of a separate case. So that would only be true for things that were negative, but then you'd have to make a separate argument for like real numbers between 2 and 0. I guess if you're just So if you like evaluated this for 0 and 2, you could probably get it that way too. This is definitely shorter. Yeah. But yes, that would work as well. It would fall under a proof by cases, which we will get to eventually, but oh, my battery is unplugged in. Do I not have any power on this table? Oh, there. I guess I just chose a bad plug.
I have to go back to that example.
Oh, yep.
So essentially what we do is plug in 2 for x, subtract that by 5, it costs -3.
Yeah, it all went off of this, the fact that our assumption of x is less than 2. So I started by subtracting 2 from both sides to get the x minus 2 is less than or equal to 0. And then if I subtract 3 from both sides here, that's where I got my x minus 5, so that I know that it's less than 0. I just subtracted 3 from both sides of this one, which, or you can think of it as starting with this one and subtracting 5 from both sides.
Yeah, that's what I was
Yeah. Yeah.
And then instead of doing
Mhm.
all we do is less than
Yeah. A -3 is less than 0. And so, yeah, sort of by transitivity then you have that x minus 5 has to be less than 0 as well. Yeah, because this one is less than -3 and -3 is less than 0, x minus 5 has to be less than 0 as well. Yeah, so what the relative ordering of numbers is another thing that you're allowed to assume. So that's, I think, again in like section 3.2, they tell you all the assumptions. So you're allowed to assume closure properties. You're allowed to do the relative order of numbers as well.
Okay.
Yeah, you're allowed to assume that. Yes?
So are these two that we've done both direct proofs?
Yes, they are direct proofs.
On the exam, do we have to write anything that's not a direct proof?
No,
Okay.
only direct proofs. Yes. So we are going to do some examples of proof by contrapositive, and today, but none of those are going to be on there. So it's only a direct proof. All right. So we've done examples with looking at things that are odd and even, that things are real, that are rational numbers. We did an inequality. Other ones that we might run across are this divides. Okay, so it's good to review this divides. So here we have if x, y, and z are integers such that x divides the sum of y and z, and x divides y, then we could conclude that x also has to divide z. Okay. Okay, so thinking about that, you know, this part of it is our hypothesis. There's two things in there. This part is our conclusion. So if you're thinking, sometimes even if you just have that in your mind, all right, well, this is the stuff I'm going to have to assume at the beginning. Right? All right, so we start there. So assume x, y, and z are integers. Okay, such that x divides y plus z and x divides y. All right. We will show that x divides z. Okay. And so just like we've done when we've had like odd or even or things like rational numbers, we always relied on the definition. That's the same thing we want to do here. So we have to think about the definition. So since x divides y plus z, okay, there exists, I'll call it a, I guess, an integer a, such that what is true? What's the definition of divides?
There's some sort of value that you multiply what's being divided by where you get what the divisor is.
Yes, good. So what am I going to multiply a by? Which one of these? X or by y plus z? No. I know, it's so tempting to want it to be, but no. Okay, it's this. So that means that I can take x and multiply it by some integer value and get y plus z. It's actually like in a denominator, so, okay, that's the thing that you'd have to divide in there. Okay, so if I divided both sides by x, okay, then I would get an integer a. So that's the idea. So if I took y plus z and I divided it by x, so x divides y plus z. And I know because it looks kind of like a fraction, you want to think about it like x divided by y plus z, but it's not that. Okay, it's actually x plus y. Okay, you would divide it by x, so x is dividing this number and you're getting an integer result. Okay, so you'd have to take this number and it has to be an integer multiple of x, so that when you divide both sides by x and you take y plus z and divide it by x, you get an integer value. Okay, really tricky. Make sure you review that definition before Tuesday. Okay, I guess similarly, since x divides z, there exists an integer b such that, okay, and this time we know that it's z equals that integer b times x.
Is it supposed to be y?
Oh, sorry, y. Thank you. Thank you, thank you. Okay. Oh, and so this is, sorry, I changed the wrong one. Y equals b times x. So that doesn't look right. Okay, there we go. All right, so I've got this one, x plus z is a multiple of x. I've got this one, y is a multiple of x. Okay, and now I need to say something about z. Well, the only place that my z shows up is here. So what do you feel like we should do? I'll call this equation 1 and this equation 2. Yep.
We substitute Bx for y in equation 1.
Yeah, so substituting 2 into 1 yields that y plus z equals ax, and so this is really bx. Yes, sorry. Okay. And then since I'm trying to make an argument about z, I probably would like to isolate z. So if I solve that for z, I'll get ax minus bx. Okay. And remember, if x divides z, then we want to be able to write z so that it's some integer times x. Okay. So, hopefully you feel like you want to do what with this?
You want to take it out,
Yeah, you want to factor it into a minus b times x. Okay. So, what would have to be true? Like once I get down to this statement, what would have to be true for me to make the claim that x divides z?
everything is, a and b are integers.
I already know that. A and b are integers. Right here. A is an integer, b is an integer. It could be, well, yeah, I mean, it could be. It does, they could be equal. I mean, it can divide zeros. Z could be 0 if it wanted to be. Doesn't matter. But what do we have to, so we know A and B are integers, but what's really important? It's almost so obvious that you're overlooking it. I said, so if we want to say that x divides z, we have to prove that z is an integer multiple of x.
Oh, so we just divide z by x.
So we have to know that what is an integer?
A
A minus b. Okay, it's not enough for me to just say that a is and b are. Yeah, I've already said that. But a minus b has to be. Yeah, okay. So, and how do we know that a minus b is an integer?
They're closed under subtraction.
Yeah, so since integers is closed under subtraction, a minus b is definitely an integer. And so, by definition, x has to divide z. Yes.
Do we not have to prove that one of them is 0 because you can't divide something with 0?
So, x is not allowed, yeah, so, well, it's just that if this is true, and if x were 0, it wouldn't be true. So when we assume that x divides this and x divides y, I mean, there's sort of an implicit, or like a indirect assumption that for those things to be true, x can't be 0. Like if you wanted to explicitly state that, it would be fine. Like for instance, if later on we needed to conclude that x wasn't 0, we could say, well, since x divides these things, it can't be 0 because 0 doesn't divide anything. But we don't need to specifically state it. But good observation. Okay. Any other questions on those ones? Okay. So, direct proof. Most straightforward, easiest kind of proof. Down. Now we have several proof techniques to go. The next one is proof by contrapositive. The nice thing is it just kind of looks like a direct proof. You just kind of change things a little bit, but it will look very much the same. It won't feel that much different. Okay. So if we have an implication H implies C, remember that that is logically equivalent to its contrapositive, where I take the negation of the conclusion implies the negation of the hypothesis. So if this one is true, this one is true. If this one is false, as if this one is false. They always have the same truth values. They're logically equivalent. Okay. So a proof by contrapositive relies on that fact and says, well, if I were to prove this, it would be exactly the same thing or equivalent to proving this one. And so sometimes it's a little bit easier to prove the contrapositive than to prove the original implication itself. But they're logically equivalent. So if I prove that the contrapositive is true, I'm still proving that the original implication is true as well. Okay. So a proof by contrapositive is basically a direct proof of the contrapositive. So it will start by assuming the negation of the conclusion is true, and then it uses arguments to conclude that the negation of the hypothesis is true. So it's just doing a proof of the contrapositive. And since that's logically equivalent to the original statement, we're actually proving that the original statement is true. Okay. All right. So let's try one. For every integer n, if n squared is odd, then n is odd. Okay, so, if we were to look at our original, this is n squared is odd, then n is odd. Okay. So if I just were to, okay, let's just try a direct proof, and I just started, I know that n squared is odd. Okay. Well, how, if I have n times n, like what do I know if n can be odd or even? It's like trying to make an argument about whether n is odd or even is very difficult, okay, from n squared. But if I knew the parity of n, if I knew it was odd or it was even, it would be pretty easy for me to say something about n squared. So going from n squared to n is difficult, but if I already know something about n, concluding something about n squared is a lot easier. Okay, so let's think about what the contrapositive of this is. So it would be like not n is odd implies not n squared is odd. Okay, and what's another way of saying not n is odd? N is even. It's just easier to think about that way. Okay, and then not n squared is odd is the same thing as n squared is even. Okay. So proving that n squared is odd implies n is odd is exactly logically equivalent to proving that if n is even, then n squared is even, which sounds a lot easier, doesn't it? Yeah, because it probably would be pretty easy to do that. Okay, so in the back of our mind, that's what we want to be thinking. Oh, this is way easier. Okay. And if you're going to use something other than a direct proof, it's a good idea to alert the person that's reading your proof, hey, I'm not using a direct proof, so get ready. Okay, so we use a proof by contrapositive to show that if n squared is odd, then n is odd. Alright, so I've already alerted my reader that I'm using a different kind of proof technique. If you're using direct proof, nobody needs to be warned about that. But other proof techniques, it's a good idea to do that. It might even be a good idea now to say, alright, so say that is, okay, we assume, okay, so thinking about the contrapositive, we're going to prove that not the conclusion of the original statement. So, we even wrote it down here so we could remember. So we assume n is even and show n squared is also even. So I've shown what my assumption is here and what I'm going to show. And just like always, I have to start from my assumptions. And from this point, essentially, it's a direct proof of this statement up here of the contrapositive. Okay, so I assumed n is even. Okay, so since n is even, what must be true? What's the definition of even?
N equals 2k.
Yeah, n equals 2k. So, since n is even, there exists an integer k such that n equals 2k. Okay. So, n squared equals 2k times 2k. Okay, and we'd like to kind of write this as, okay, we want to show that this is even, so if I can write it as 2 times something else, that will get me what I need. Alright, so in here I would need like a 2k squared. Okay, so I've taken n squared, and if I show that I've written it as 2 times some integer, I'm good. So what's the only thing left to do? N squared needs to be 2 times some integer. So, n squared is 2 times, do I know that's an integer? Could I make an argument that it's an integer? Yeah. Okay, why is it an integer? Under? Yeah, good. Okay, so because integers are closed under multiplication, 2k squared has to be an integer, thus by definition, n squared is even. As I've written it as 2 times some integer. Okay. So the closure properties come up over and over again, don't they? You always have to show that, okay, that has to be an integer for me to really make a convincing argument that it's true. Okay. All right, so the proof by contrapositive, way easier than trying to go at it directly, just because I knew n squared is being odd, okay, and getting n squared as some kind of 2k plus 1, and then trying to figure out what n was. It's like you'd have to factor it into the, it just doesn't work well, right? The other way, super easy. Okay. All right, let's try this one. So if n squared is not divisible by 4, then n is odd. Okay, so n squared not being not divisible by 4, that's like saying that n squared cannot evenly be divided by 4. Like 4 does not divide n squared, so n squared is not divisible by 4. That's another way of writing that. Okay, then n is odd. Okay. So that's what we're trying to prove. Okay, well n squared is not divisible by 4. That's a kind of tricky thing to think about. Okay, well, let's think about the contrapositive. So what would the contrapositive be? Yep, sorry. What would the contrapositive be? Yeah, what's another way to say that? Yeah, so if n is even, yeah, then 4 divides n squared. Way easier to think about, right? Because we know the definition for divides. That would be okay, but if it doesn't divide, then, you know, I just know that something is not equal to, it's a little bit tricky. So this one is a little bit tricky to think about. This one is easy. Okay, so definitely looking at the contrapositive is going to be way easier to reason about than the original statement. Okay, so And we use a proof by contrapositive. That is, we assume that n is even, and we will show that 4 divides n squared. Okay. So here is our assumption that n is even. So since n is even, what can we conclude? Okay, good. So there exists an integer k such that n equals 2k. All right, now we're trying to show that n squared can be written as 4 times some integer, right? So let's think about that. That's where we're trying to get to. So we're trying to like make an argument about n squared. So let's come up with an expression for n squared. So n squared is 2k times 2k, which is 4k squared. Okay, I'll even maybe just put parentheses around this. So remember, if we wanted to make an argument that 4 divides n squared, we have to be able to write n squared as some integer multiple of 4, as 4 times some integer. So is n squared equal to 4 times some integer is the question. And what do we have to prove to show that yes, indeed, it is in the exact form that I need it to be? Yeah, so since z is closed under multiplication, what must be true? What has to be an integer? What's the important thing that needs to be an integer? K squared, that's right. Okay, and so since this is an integer, I've now written n squared as 4 times some integer, and that's the definition of divides, right? So by definition, 4 divides n squared. Everybody got that one? We've got time for one more, and we'll call it a day. All right. For every pair of integers x and y, if the product xy is even, then x is even or y is even. Okay, so we have xy being even implies that x is even or y is even. That's kind of what we have. Okay. And that doesn't seem like too bad. The thing that's difficult is if we know something about the parities of x and y, it's a lot easier to argue about the product than if we know about the product arguing about x and the parity of x or y. Also, just this or is a little tricky as well, because for this statement to be true, either x is even is true and y is even is false, or x even is false, y even is true, or they're both true. So there's like 3 different things that make this true. So that makes it a little bit tricky too. So just because this is even, we'd have to show, well, there's 3 different ways that this thing can be true. That can be a little bit tricky. Let's look at the contrapositive though. So what's the contrapositive? X is odd and y is odd. And there's only one way for that to be true. Both of them have to be odd. Okay, implies, and then xy is odd. Okay, much, much easier. So there's only one possible way for this conjunction to be true, is if both of these are true. And then I know about the parodies. This is supposed to say y. I know about the parodies of x and y. I probably maybe even have at some point proved this. Maybe you guys did it in on side books or something. All right, but definitely the contrapositive is going to be way easier. So we use a proof by contrapositive. Okay, so we'll assume that x and y are odd and show that xy is also odd. Okay. So since x and y are odd, there exist, we'll just let's call them, shall we call them A and B, K and M, well, A and B. Integers A and B such that what is true? What's the definition of odd? Yep, 2a plus 1, and y is going to be 2b plus 1. Okay. And then I say, all right, well, what am I trying to prove again? Oh, I'm trying to prove that x times y is odd. So I better come up with an expression for x times y. All right. So then x times y is 2a plus 1 times 2b plus 1. All right, so that is, what, 4ab plus 2a plus 2b plus 1. And my goal is to get that xy is odd. Okay, so remember, odd, it should be 2 times some integer plus 1. I have this nice plus 1, so could I write this as 2 times some integer plus 1?
Yeah.
Yeah, what would go in there? On?
It will be 2ab plus a plus b.
Good. All right. So, I know that this is odd if I can write it as 2 times an integer plus 1. So what's the last thing that I have to do?
Prove that 2ab plus a plus b is an integer.
Good. And is it?
Yes.
Because?
It is closed under multiplication and addition.
Good. So since the integers are closed under addition and multiplication, 2ab plus a plus b has to be an integer, and by definition xy is odd. All right. So we have a new proof technique, but really it's just a direct proof of the contrapositive, right? So it still feels just like a direct proof. It shouldn't feel scary. It just feels the same. Okay. All right. So there will be a direct proof on the test. There's just one of them. So just be prepared for a direct proof. We've done lots and lots of examples now. I know you guys have the flow of what they look like. If you have come up with any questions before next Tuesday, shoot me an email or... The exam is on Tuesday. It's on Tuesday.